because the way the class is progressing, and on Tuesday there is no class. I mean, even though I'm gonna upload the video lecture and everything, but still no in-person contact with you guys, right? So we really have to move a little fast, okay? So first of all, there will be a new homework, right? The homework 6 is probably due today, so I'd be expecting it's due today, right? The homework 6, actually homework 7, right? Not homework 6, homework 7, right? It's 7 or 6? 7, 7. Yep. Yeah. So I split it one homework to two. That's why it's like every year it's kind of changed. So
The due date of homework 7 does say it was due on Tuesday.
oh, it was due before. Okay. So is there any more homework there?
No, it's just 1 through 7.
Okay. So yeah, after this class, I'm gonna upload another one. Okay. So that one is like the thing that I started. Okay. So today, hang tight. We gotta cover a lot of things. Okay. I'll try to be not too fast, right? But make sure everybody's with me. But it needs to be finished. A lot of materials. Okay. I don't know how, but magically or whatever, I gotta finish two problems. Okay. But the issue here, you gotta understand those equation manuals, right? Remember, I started on that in last class, right? I'm gonna talk a little bit on that. Okay, so that's one agenda for sure. The other one is the final project. So I'm gonna talk a little bit about the final project today. Around this time every year, I started talking about the final project. Otherwise, the students gonna feel overwhelmed at the very end. Okay, so basically, if you have some knowledge about the final project today, and if your time allows, after at the end of the class, if you can just walk with me in the lab, I'm gonna show it to you. Okay, what you're gonna do, that would be great. Okay, and I'll after this class upload the final project materials and the homework number 8. Okay, is it clear? Don't spend any more time on that. Okay, so now move on to the final project thing first. Okay, the final project, remember, I did talk about is a transient heat transfer problem. You guys remember the transient heat transfer problem from exam 2? What happened? That is this part number. You need to first try to see if that is less than 0.1, and then you can see you can use the long capacitance method, right? And then you had this temperature distribution equation. Does it ring a bell? What I'm saying, everybody? So you had this temperature distribution equation, right? And you had on the right side, you have this capacitance, you have this thermal resistance. Okay, they call time constant. Does it ring about time constant? Yeah, tau t. Okay, t. So those sort of thing. Okay, all those things will be required for this kind of project. Okay. Now let me give you the overview or layman term. I mean, without any complicated theory or anything. Okay, think this way. So say you'll be given with a block, okay, and you'll be given a thermocouple attached in the middle somewhere of the block. Okay, what you'll be doing, let me explain it to you first, and then I'll gonna come to the theory. Okay, man. So see, like this block the block is standing on a rod kind of a thing. You'll be seeing in the lab here, somewhere like that. Okay, and then I'll be giving you a hot gun. You're gonna heat it up to a certain temperature, say like 45 or 60 degrees Celsius. Make sense? Okay, so once it heat it up, okay, you'll leave it somewhere out. Okay, not even internal or anywhere, somewhere out, and you're gonna have a stopwatch. You're gonna start recording the time, okay, until this block temperature is close to the room temperature. Now, if you're gonna get it to the room temperature, it is gonna take forever. Means like hours and hours. But we're gonna assume, okay, if it starts from 60 degrees Celsius, and you'll be happy when the temperature becomes like I don't know 28 or 30, okay, which is still hot, but not the room temperature. Room temperature could be 25 today, right? Inside of 23, I don't know. But to get it to 23, it would be horrible. It will take a long, long time, right? But to get it like, I don't know, 28 or 30, it don't take that much of time. But that is enough. That's the point I'm trying to make here, okay? You don't necessarily need to get this temperature to 23 or room temperature. If you're going to get it to 30 or 28, that is enough. Okay, but that doesn't mean you're gonna stop taking the data when the temperature comes to 60 to 45. You're gonna do that. I'm gonna take out parts. Okay, so you're gonna start to take out. You're gonna start to get the temperature readings and write it somewhere. I have a standard, Excel or this table okay, made by Word. I'm gonna provide it to you. So Hey, Harry. So I'm gonna provide it to you. So you're gonna start filling it out. Okay. So that part you understand. That's so easy. Like you raise the temperature. You have a stopwatch. You started recording the temperature. By the way, how to record the temperature? So I'm gonna give you a thermocouple meter, or I'll tell you at least like what to get it. So you're gonna get it different times when you're gonna do the experiment. You get the thermocouple meter. You're gonna get the reading of the temperature when you're gonna start to write. So you have this stopwatch and the thermocouple meter. Two things: the time and the temperature. Time and the temperature. You're gonna write until from 62. The temperature I was saying like maybe 30 or 28. Not necessarily anything above. Okay, I won't be long. Okay, once you have the temperature, I'm explaining the data taking first. Okay, so once you have the temperature, you have done one part of this experiment. Okay, there are more parts. What are those? So this thing that you just did, you are exploring the natural convection. Why? Because the block is sitting outside, right? You don't have a fan or anything that helps cool it down. Does it make sense? So it's natural convection. So in situated convection, you might be wondering what is natural convection, what is forced convection. But by the way, sometimes people say free convection. It's the same thing, free and natural. Okay. All right. So natural or free convection, it happens not by external draft of air, right, David? How does it happen? The natural or free convection by the density gradient. What the density gradient happens? You might be learning it from early school age, right? Doing experiments, right? If you are boiling water, when the water is heated up, the density becomes less. Remember that? And then, heavier water, which is high dense water, always comes from the top to bottom, and the lighter water, when it's heated more, it's going up, right? And then the heavier water become heated again, and it's become more thin because it's less dense now. It's going to go up, and the heavier water from up to come down to heat up again. Does it make sense? You remember that from science class? Okay, so what the idea here is like, heavy things usually go down, lighter things usually go up, right? And things get lighter when you heat it up. Okay, so the same principle here on the pure natural convection. The air, right? Isaac, around it, we're gonna get heated up, right? When this block is heated, when the block has high temperature, what happened with the air? When it's light up, it's gonna start to rise, right? It's gonna start to rise because it's lighter, right? Lighter air, like helium balloon, like it's going up because it's lighter, right? We know that, right? So what happened? There won't be any empty space. There's no way there's a vacuum. The heavier air is gonna come from the side, right? It's gonna heat up, it's gonna go up. So there would be like something similar to like, take a look what is happening. So something similar to like, you see, so air is gonna go like this, right? Does it make sense? So this is what happening without forcing the air movement around it by external means. This is happening naturally. And naturally means due to the density gradient. You see the change of the density happening due to the temperature of the block. It is happening because of that, naturally, right? That's why people call it natural convection. Sometimes they call free convection. Okay? And on the contrast, other thing is that forced convection, right? Yes.
Are we allowed to use coded circuits?
Coded circuit?
Coded circuits for like tracking the time over temperature.
Go.
I kind of already have one of those from a previous project.
Go nuts. Yeah. All right. So you understand that free convection every day? So that's one part of the experiment. And that's very exciting thing that you'll be doing for the project. Okay. The first time you'll be seeing relating the equation with the actual experiment. Okay. So the second one, I shouldn't say second one, the second part is the force convection. And the force name itself says that you're going to use a fan, okay? You're going to use a fan to move the air around the block, right? Harley? Move the air around the block. What happened when the air is moving around the block? You're expecting the heat transfer faster or lower? Faster, right? You're going to make sure the hot air around it is going to move, and new air is going to come with cold, and faster way it is going to get cold, right? So in other words, when you're going to deal with the fan of forced convection, this experiment, the same one, will not going to take that much time. It will be much faster. So like you raise the temperature for this block to 60 degrees, And the same thing you want to do for free convection, like taking it down to 30 or 28 degrees Celsius, it is going to take possibly 1/4 of the time or even less because you're running a fan, right? And why would we doing it? We do have a perfect place for that, which is our wind tunnel. Anybody use the wind tunnel before? It's so easy and straightforward. At the end of the wind tunnel, you'll be seeing a big fan there, and there is a knob over there, and on that knob you can control the speed of the fan. So basically, say like you turn it on, it's on certain speed, and the wind is coming, and it's lowering down the temperature much faster. You are recording the same thing, right? The temperature and the time, right? From 60 to 28. So that's one experiment, right? What if you have a means to change the fan speed or different end speed that is coming on the block? So if initially we have say like 5 meters per second, air is coming around the block, that will be one situation. And then if we ramp up the speed, say like 10 meters per second, air is coming around the block. So that is much faster. And your common sense tells you that way it will be much faster cooling as well, right? That's what common sense tells you, right? More of the speed of the fan, more of the cooling will be happening, and the more of the H value. Your common sense tells you that, like unless the layman people, they don't probably understand the H. You know H, right? You know, more the H, more the heat transfer, right? More the fan speed, more the H, right? More the heat transfer. You understand? So what is it that you are trying to achieve here? By exploring those time temperature relation you see on the Lamb capacitance method that you did in exam 2, by exploring that equation, you'd be finding the value of the H, right? For all those different situations. Like what are the different situations? Like the fan speed, if you're going to change it to say like 3 speed, you have 3 situations, right? If you're going to change it to 2 speed, you have 2 situations, right? And without fan, you have 1 situation. So it's three situations already, right? So these 3 experiments you'll be doing. There are other dimensions I actually put it on the experiment project, which is the block is not a round block. The block was like a block, like a cube. Okay, so if the cube get exposed, right, horizontally, then you would be getting one kind of edge. If you flip it and make it 45-degree angle on the fan, see if it is making any difference or not. Okay, so basically the orientation from 90-degree exposed to 45-degree exposed, right? And if you're using 2 fan speed, then you will have 2 more experiments, like 5 experiments, right? Basically, you have to not do it alone. The data reading part, but the calculation you gotta do it alone. Now, when you're doing the calculations and writing the report itself, maybe you can work as a group of each other. I don't mind, but you gotta do it. Okay. The idea here is everybody do it by themselves, so everybody get experience what is actually happening in terms of the math. Not like copying others. Rather, you talk as a group. Okay. You work together. You help each other and finish the project, but everybody has to submit separate report. But as long as if you're doing it by yourself, no matter how hard you try, it won't be copying the others. It will never be match. It is impossible. So if I'm gonna see anything matches with other, you're gonna expecting a 0 for both of you, right? You don't want to do that. Basically, I'm just encouraging you to do your work. But I'm encouraging at the same time, work as a group. Take help from your friends, doesn't matter. Take help from me. Okay, I'm gonna help you also. But do the writing, but data taking do everybody in 2 different groups. So split into 2 different groups. This is the time for you to split into 2 different groups, right? Alright. You can talk with each other. Okay. You are gonna split into 2 groups like this way. This 2 sides. No. Whatever we're gonna do. I'm assuming David, Matt, and Isaac will be one group, right? And Harley wanna be with them. Okay, say like Harley's group, like I'm assuming Michu gonna come. I did see him around. So like 5 of you, right? 1, 2, 3, 4, 5. No, 6, not a 5. And rest like Logan, Steve, Jefu, Chelsea. Yeah.
I think Logan agreed to be on Isaac.
Yeah, me and Matt.
Everybody's they need some people here as well. So then you guys have to split up. Logan and David needs to be in 2 different groups. And now you gotta decide we're gonna be which group, okay? Or Steve and Logan needs to be 2 different groups. Okay, then you gotta decide how you're gonna make the group. I don't wanna interfere. You talk with each other, okay? If Logan will gonna be in your group, then Steve, Steve needs 5 people, okay? So maybe then Harley's group needs to be with Steve, right? Harley and Mitch needs to be with Steve. You decide. And if you don't like the group arrangement I did, do it in your own. But make sure it's split into 5 and 5. We have 10 people, but it could be like 5. One student never showed up, like Madeline. Don't even bother to get her. But other than that, we have 9 people, so 5 and 4. I want to say 5 and 4, no more than 5 in one group. You decide. I give some suggestions. Not necessarily you have to stick with that. Okay. Every year they decide. I have actually never decided.
Am I allowed to be in the group for you?
You guys decide. If I'm going to interfere any further, it is not good, right? You're not going to like it. So why don't you guys decide? Why I'll be the bad guy? Okay, you be decide. Okay. All right. You are allowed to be anyone on this group. Okay, as long as you guys are coming in. So the max could be 5 and 4. Okay, 5 and 4. All right, so you guys understand it's very important the next class, right? Next class I'm gonna actually show you the project. Today I'll introduce you briefly, right? But today's class is also very important. I know Mitch and others are not here, Difu, but hopefully they are watching. They will be watching the video lecture. I'm gonna send a email to all of them. All right. So the next thing, everybody, you guys are ready, right? So these are the theory. I don't want to talk. These are the theory for the project. I don't want to talk about it now because I have some more things to cover. Okay, equation manual, right? Everybody come back here, okay? I'm gonna this time go a little faster because I think I give you enough intro already, right, Harley? Harley, get pen and paper, okay? Focus on these things. So many things are gonna happen. You're gonna get bombarded with so many things shortly. You can get time to catch up, okay? All right, so let me be very clear. When I'm showing you the equation manual, you're not going to have time to write anything because my goal here is to just point out the equation manual, give you the understanding first, okay, verbally, nothing in writing. But I do have 2 math problems, which would be a goal, a very optimistic goal. I'll try to solve 2 math problems. Other than that, there is no way you can do the exam or anything, okay? There is no time, okay? All right, so okay, equal to. All right, okay, so let's try to understand the basic first. So these are the things you can write. So laminar, just the keyword. I'm writing the keyword: turbulent, isothermal, okay, constant heat flux. This keyword you can write it, okay? I don't mind, okay? These are so important. Okay, so the other thing could be liquid metal, and flow around a object. Now this object could be a cylinder or any object. Okay, these are the keyword, okay? Let's try to understand them first. Okay, and as I said, this is optional for you to write, but these keywords, maybe you want to write, everybody. These keywords, if you understand those keywords, then once I'm going to start to give you the understanding and then understanding the equations, then you'll feel comfortable, okay? You'll feel comfortable. You must need to know the equations and the whole picture first before jumping to the math problem, okay? Then you can decide where to go to find the equation, which equation to use. So you should be ready. To be like that, like finding the perfect equation. Okay, once you're done with those keywords, now let's focus. Okay. First thing, laminar and turbulent. Everybody knows this. We did talk about it. That's so straightforward. Now I'm gonna draw. You just focus on this. Okay. You don't have to write anything. Okay. If you're gonna start to write, you can focus what I'm saying. Just focus what I'm saying very, very, very minutely. So you have laminar and turbulent. If you have an external flow, anytime I see external flow, I'm gonna draw a plate. Okay, on the external flow, you have these two different sections. This one is laminar, LAM means laminar, TURB means turbulent. Okay, so these two sections. Okay, I'm gonna do overview as well, right? So, and the transition happen usually at Reynolds number XC, which is 500,000 as per Incropera. I did talk about it. Okay, and when the transition happen, you definitely know the heat transfer here and heat transfer here are different. That means you have in this zone H laminar and in this zone H turbulent. Okay, we did math here, did everything like homework and everything. We do know that. Now, when we don't have a bar on the top, that means there's the local H. That means it could be at any point. And when you have a bar on the top, that means it is the averages. That means it's the average of that whole thing, right? So everyone remember up to this, these are important. Okay, so now let's focus on these two things. Okay, so isothermal and a constant heat flux. I would like to start with the example, okay, or application, I would say. So isothermal, as in last class I was saying, assume this temperature of this block is same or constant at every point that you can think of or measure of, right? Which is practically now, right? Every point this block does at the same temperature, right? So the practical application to tell you the heat transfer for this kind of layers, right? The boundary layers would be you hold a heat gun here, right? And then heat gun is doing what? Like high temperature on the top of this plate. The plate temperature is still same here to here initially, right? If you're gonna, steady state and transit, everybody know that. Steady state means what? As if like you're taking a picture. And you just have one scenario at a certain point, right, Harley? So before any type of heat transfer happen, before any type of building happen on the boundary layer, the temperature of this thing will be same, right? Same as room temperature, right? So that's the steady state condition, and that's the practical application of this isothermal. Everyone understand isothermal? The other application of the isothermal I would like to give you, say like you have a ice water bath. Everybody use ice water bath time to time, right? If you're gonna, tired and try to suck your feet on an ice water bath, people do that in a warm place, not in North Country, in Florida, or if you're gonna go Mexico, it's common. All right. So I was just saying, like in a tired, very very sunny day, you may want to do that. So ice water bath, bottom line, has ice and water all maintain one single temperature. Now the ice itself, if you're gonna dig through inside, the temperature could be lower, but the water that is floating, the ice that is floating on the water, if every corner you're gonna put a thermoprobe or thermocouple anywhere, you'll be seeing the temperature what? 32 or 0. Does it make sense? So that's another application of isothermal. Okay, isothermal. All right. So now move to the constant heat flux. The constant heat flux example. I'd like to start with the application first. Every day, almost every day, any household it use is a stove, right? If you turn on the stove, okay, to a certain setting, there is a constant heat flux to that setting, okay, because you are heating up the stove at a certain rate, okay. No matter how big of the pan that you are using, still the setting, if it's medium, it is giving you a certain amount of heat flux, right? Wattage. Does it make sense? All right. So that's the constant heat flux example. You understand? All right. So now that you understand these two scenarios, now that you understand the laminar turbulence, now that you understand the transition happened at Reynolds number critical and everything you remember. Now that you understand the average, now that you understand the local age, everyone understand everything, right? Now you are actually ready for this table, right? Now let's talk a little bit more about the table. You're gonna see a lot of tables here. So the title of the table has, sometimes it has isothermal laminar, sometimes it has isothermal turbulent, sometimes it has constant heat flux laminar, sometimes it has constant heat flux turbulent. Let's try to match whether we do have that or not. So come back here. Okay. So you see, okay, so this table title is what? Laminar isothermal. Everybody's agree, right? So there are a bunch of equations. Don't worry about that now. I'll talk about it later. This table, what is the title? Laminar constant heat flux, right? All right. Now this table, what is the title? Turbulent isothermal, right? You see that? Now I do have that thing and this film temperature. I'll talk about it more. But for now, focus on this. This table, what is the title? Turbulent constant heat flux, right? All right, now that you have those 4 tables, everybody understand those 4 tables. Now I'll focus on these 2 tables, right? Time is running so fast. It's very difficult to do tonight. At the same time, not like very fast. At the same time, you're seeing I'm trying to cover so many materials, right? The project I give you the understanding, now the tables I'm trying to give you the understanding. Stop me anytime if you feel like I'm going fast, because this can be go fast and you know not understanding. You have to understand it. You know where. All right. So now I was just saying, like, let's talk about 2 tables first. Okay. Let's start with the easy one. The combination could be laminar constant temperature, right? Or isothermal temperature. Okay. Let's talk about that table. On that table, what are the equations that you're seeing? So I was just talking about this table. So not this one even. I was just talking about this table, right? And there are some things that I write here, forget about this. I'll just focus on this, okay? First of all, what is the film temperature? Everybody need to understand the film temperature, TF, okay? They think this thing is called film temperature. You want to write it. In the book, they have this. So what is the film temperature and why do we need that, okay? Let's try to understand that. Everybody focus here. So the film temperature means, say like you have an isothermal plate, like this plate has here, Isaac, say like 25 degrees Celsius, and the hot air is coming 45 degrees Celsius, right? So the film temperature is the average of those 2 temperatures. What? Like 45 and 25. That's what I said, right? So you need to get this temperature for what reason? Remember, you have to find the Reynolds number, Prandtl number, those as thermophysical properties. Like what? Reynolds number does have the mu, rho, no, Prandtl number does have, like, alpha, mu, but it is Prandtl number itself, you can find it. But those are for thermophysical property, right? Right? So that thermophysical property, varies by temperature. Right, is it? So you need to know a temperature, what temperature you need to find those properties. Steve, you got it? So that temperature is called what temperature? Film temperature. Do you remember? So now you understand. So now let's focus more on this table, right? So we're dealing with what? Chelsea, understand, right? We are dealing with laminar and isothermal. I said I don't have time to write any of the equation, but still I'm gonna write these 2 equations for first time. Okay, I won't be writing any more equations. Just I promise. Okay, these 2 equations I want everybody to write. So you're gonna have some practice. Okay, so what are those 2 equations? So Nusselt number 0.332, Reynolds number half, Prandtl number 1/3. I want everybody to write this equation. Matt, write this equation. Write it. So you're gonna have a practice. You're gonna use it shortly. Okay? Write it. Everybody write this equation. Okay. Once you're gonna write it, you're gonna strike in your brain what you are writing. Okay. So you are writing obviously Nusselt number, Prandtl number, and Reynolds number, right? So if you don't start to write now, then at some point you won't know what is Prandtl. So Prandtl is PR. Okay. So Reynolds is RE, Nusselt is NU. Remember that, okay? All right. So now, once you finish writing that, just immediately something come up in your mind. Okay, I don't have a bar on the top of NU. What does it mean? I'm talking about the local or average. I'm talking about the local Nusselt number. Do you understand that? What does local Nusselt number gives me? The local Nusselt number gives me the local H or local heat transfer coefficient. What can I find by local heat transfer coefficient, Isaac? I can find the local Q at any point. Okay? So everyone understand that? Okay. So what is that we're seeing? I'm sorry, this is PR to the power 1/3. Okay, well, I did write very good over there. It is for some reason every time bad way it is reflecting. This needs to be changed. Okay? Just want to give you a clarification. Okay, so see the Reynolds has a X. This is subscript. Nusselt has an X on the subscript. What does it refer to? X. What do you think? You have to understand that as well, okay? You don't know. Let me explain it. Okay, so what is happening here? See, from this end, as if like, okay, Max, focus on that. From this end, if X value is 0, say like the X value here at this point, you are interested to find the H, right? Of the Nusselt number. So that is that X that they are after. Okay, from this point to this point, what is the value of the X? You understand? All right. So that means that local H or local Q are found at this point. So that is the reason they have this X. Now, you will be seeing oftentimes instead of X, they write NUL-REL. L means what? L means the length. Usually by the symbol L, okay, Matt, what they are referring? The whole length of the plate. Everyone understand? If you're going to see the L, what does it mean? The length of the plate, right? Logan? Understand? If you are seeing the X, that means it could be any point in the plate, right? Everyone got it? Everyone got it? Good, right? All right. So what if I'm gonna put this bar on the top? Take a look here. If I'm gonna put a bar on the top, this value is no longer 0.332. What is that value now? It's twice. Okay. So that if you are interested to find the average Nusselt number, this is twice. Okay. And you might notice here already. Focus on that. You might notice here already the Nusselt number. If you have a bar, you have a H bar here. H bar X divided by K. If you don't have a bar, H X over K. Now here's the point: HX or H bar X. What they're referring by X? They're referring by X for these two situations. As I focus on that, so say like if it is HX, that means at this point HX, right? Say like this is H bar X. That means if this is X, from here to here, this is the whole thing they're referring. Make sense now? See me explaining too much in one table. There is a reason behind that. Once you understand that one table without any confusion, you'll be able to understand every table. Understand? So seeing me, that's the reason you're probably seeing me talking too much, too detailed. I have to make sure everyone understands everything, okay? So in one table, if everyone understands everything, then the rest of the table, you can explore it by yourself, okay? You don't need me, okay? So again, this bar thing, everybody clear? Without bar, everybody clear? The X thing clear? The L thing clear? L is for the whole plate, right? Plot length, right? This equation, this power is clear, 1 over half the power 1/3, right? And these are the power, it varies based on the tables, right? Okay. So you guys are all clear about these two equations. Where do you find this equation? You see this equation number from the book, right? Here, and these are the conditions, right? You guys remember the Prandtl number 0.6 is or above is for water, for air or more, right? For water, everything it goes with that, right? All right. So now let's focus on this. Liquid metal. Let me talk about that. And I do have the keyword here. What did I write the keywords? Liquid metal. All right. So liquid metal is a special situation, as if like you're working in a foundry. Anybody ever been to a foundry? I was like, when I was doing undergrad, we used to have a foundry lab. We used to make like, different. We had a cast. We used to make using this cast like different shapes of metal, right? In a foundry, they call the whole thing as a foundry, right? The shop is like foundry, okay? So in a foundry, you'll be seeing like this kind of thing, like the liquid metal flow, right? Obviously, the liquid metal means what? See, like it's so much temperature, right? So the heat transfer will be so much, right? You understand the common sense is going to tell you that, right? And liquid metal, unlike the fluid, like liquid metal is also fluid, right? But unlike the air or water, right, it doesn't move that. The viscosity is way too high, right? So the action won't be similar to like other standard fluid like air, water, or whatever you're dealing with, right? So for that, they have a complex equation, and you'd be dealing with this thing in homework and in exam as well. I'd like to give you a heads up using this equation. Using what is this liquid metal equation? Okay, using these two equations, okay, for liquid metal. Okay, I'm gonna take out everything. Just focus on this liquid metal. So first of all, you have liquid metal, and then you have this local Nusselt number and average Nusselt number, two different equations. Okay, and you see on the subscript, I have this liquid metal along with whatever you had before, right? And then you see on the right side, I have a complex equation, right? Okay. On the right side, I have a complex equation. Now take a look on that equation. Does it look really so scary? It does. But if you're gonna try to find the value of the Nusselt number for liquid metal, if you know the Reynolds and Prandtl, it's just algebra, right? It does look scary, but it's not too bad, right? It's just algebra. You just have to plug the values into getting the Nusselt number, and from there you know Nusselt number is like this. You can find the value of the H. From the H you can find the value of the Q, right? Is it clear to everyone? And you need both local and the average, right? And for average, you don't have to explore the local again because it's twice the local, right? I do have that. So does everybody understand this table? If you understand this table, you can literally explore all other tables. But I'm going to explain a little bit more with the turbulent table as well because it is a little exception. Why? Think about this way. You see, when the fluid is flowing on the top of a flat plate, take a look here. So you have first few meter or whatever has the laminar and then the turbulent, right? I said so laminar and then the turbulent, right? So now if you're trying to find the local H for turbulent, say like here where the turbulent is there, right? You can use the local H equation for the turbulent. However, if we're interested to find still at that point, the average H, then the problem is going to happen. Why? Anybody can tell? You have a little bit of laminar here, right? So you have a mixed layer. That's why they call this thing mixed layer, where you have laminar and turbulent, right? When you're trying to find what? Average H, right? Or average Nusselt. But if you're trying to find local H here or local Nusselt number here, you don't care what is happening here. Then you can use the turbulent equation from that point, right? Everybody understand that? Now let's try to focus on the equation now. I gotta go really fast on the math now, otherwise I can get tired. All right, so here, so this is laminar steel. Do you see what is that? Constant heat flux, laminar. Everybody can understand this without my help? I'm assuming. All right, now this one you need my help for sure. Let me take out everything that whatever you're seeing here. Okay, let's just focus on this. Okay, so this thing, turbulent isothermal, right? And you have this laminar turbulent, right? You have this surface temperature Ts. You have this Xc. What is Xc, Logan? Where the transition happened, right? From laminar to turbulent. You have this U infinity, T infinity for the year. You have this total length is L. Everybody understand this whole table? Okay, so no, not the table, like this is catch. Okay, what is this TF, David? Film temperature, right? How do you find the film temperature, Chelsea?
It's the average of the surface versus the surrounding.
Yeah, surface and the ER around it, right? So that is important. Why do you need the TF, Logan? We need it for getting the property values, right? Like mu, rho, Cp, whatever your Prandtl number, right? We need that for that reason. Okay, so now let's focus on that. So first of all, there is this lambda. What is lambda again? Delta. I'm sorry. I'm saying lambda. Delta. What is delta again? Yeah, the delta is the boundary layer thickness. Boundary layer thickness. We have delta and delta T, the homework that you are doing, right? So that's delta and delta T. What is that you are seeing delta and delta T relationship for turbulent? Is there any Prandtl number relationship? No. So it's the same. Remember that. For turbulent, it's the same. Why? For turbulent, the heat transfer, because of the chaos of the fluid moving all around, the boundary layer would be same. Okay. Why? It's another explanation. I'm going to skip that. So local Nusselt number and average Nusselt number. You see. So you do have, this one is so important. So you have this local number, Nusselt number, average Nusselt number, and average Nusselt number twice. You have one time average Nusselt number, two time average Nusselt number. For the second time, the average Nusselt number, it is mixed boundary layer. For the first time, the average Nusselt number, it is not mixed. What does it mean? Let's try to focus on the average Nusselt number, right? The local is going to talk later. So would you have two different equations for average Nusselt number? you know why I'm giving you the pause so that you can think a little. You're thinking, right? So why do you have the two different average national number? Why? What is the purpose of that? Think this way. Isaac, think this way. Say like we have a cyclone coming on the top of the table. Are you expecting any laminar march at the beginning? You should, but that could be a very small, tiny part of it, or because of the disturbance, it is almost non-existent, right? So you'd be expecting the whole plate has turbulence. Does it make sense? That's your assumption. In that case, are you going for the mixed layer equation? No. Now, I gave you the hurricane is the extreme case, tornado is the extreme case. Maybe not those things are coming. Maybe very high velocity is coming. Maybe there is a trip, right? Maybe this surface is rough, right? If this surface is rough, probably the turbulence will gonna begin. Just you understand? From the very beginning, there is no laminar. It is too rough, right? It makes sense? From the very beginning. So the average Nusselt number equation, I think you got it. This one, the first one that you are seeing here, will be applicable for that special situation, right? But in a regular situation where the fluid flow is not that high, okay, you have a smooth surface, you would be expecting a laminar flow and then a turbulent flow, right? That's a mixed layer. You understand that? For the mixed layer, this is the equation. Okay, what is that equation? Take a look here. So I know for some reason this thing sucks, okay? That's why you're not seeing it clearly. So what is that equation? This is the Nusselt number. I'm gonna make sure from next semester on they're gonna fix it, okay? I'm gonna make the first in this office. See the Nusselt number L means for the whole plate, right? Because the average you are interested is equal 0.037 Reynolds number to the power 4 power 5, right? Minus A, then the whole thing Prandtl number 1 over third. Now what is this A? A has a big equation, but you don't have to worry about that. You can simply use the value of the A is 871. And that big equation, if you're going to solve it, is based on the critical Reynolds number, 500,000, okay? You'll be getting the A value 871 anyway, okay? So basically, that equation does have this A, and A is 871. That is not a complex equation anymore. And that's my review of the equation method. Why I'm saying that? Because you see, the local turbulence is the same as the local laminar, right? The average turbulence, you understand two situations. One is everything is turbulent, then the first equation, right, Isaac? And if you have like laminar and turbulence, then this is the equation, okay? And this one is for laminar and constant surface temperature, right? Now it could be constant laminar. Sorry, this one is like turbulent constant surface temperature. This could be like turbulent constant heat flux. This could be like laminar and constant heat flux. There are two more tables, right? Everybody able to understand those tables by yourself, right? I probably can do just one man problem. Right? It's alright. I don't know. Make it fast or do anything like that. But we're gonna do it such a way that you understand. Now I do have 4 math problems uploaded in Brightspace. Okay, I'd like everybody, and those are solved. Okay, I'd like everybody, and one of them I'm gonna solve it now. I'd like everyone to at least start reviewing them. You're gonna start reviewing them, understand the table that I explained, understand the math that I was gonna be about to do, right? You should be able to start with the homework. Okay, and on Tuesday, next week there won't be any class. Tuesday and Thursday, because I'm in the conference. So what will happen? So
No, the exam is the week after on the 22nd.
yeah, that exam is on Monday, I said. Thursday. I can do Monday because I'm gonna do review and everything, right? So so this thing is like week 13, right? When I'm gonna come back next week is week 12, right? Yes, so week 13. You see what? So the project, guys, don't feel stressed, okay? I mean, I'll be here in my office. If you're interested, I can show you what to do in person this week. So this is gonna get out from your head. So on week 13 you can do exam 3, and week 15 you can do exam 5, right? Your choice, okay? And by this next week you can finish the homework that I upload, and that homework and homework number 6, those are for exam 3. Okay. So if you're gonna deal with those 2 homework, you should be good for exam.
6 and 7.
No, 7.
No,
You're doing
7.
7 and 8 then. 7 and 8, right? The 8 I'm gonna upload now. Okay. 8 and the project, both I'm gonna upload immediately after this class. Okay. I don't have anything after this class. I have meetings and other stuff, but not any class. Okay. Alright, so come back. I gotta be at least one problem, right? Everyone understand the tables? Okay. Alright, let me do one problem. See if you can feel excited. Okay, so I'm not gonna do that one. I'm gonna do this one. All right, problem number 2. Let's focus on this. By the way, these are final project stuff. Okay, we'll talk more about it. Okay, in person with you guys. All right. So during a cold winter day, wind at 55 kilometer per hour is blowing parallel to 4-meter high and 10-meter long wall in a house. If the air outside is 5 degrees Celsius, right, and the surface temperature of the wall is 12 degrees Celsius, right, determine the rate of the heat loss from the wall by convection. Okay. All right. When the air is coming on the side of the house that you're seeing, that side dimensions are given 4-meter by 10-meter, right? You'd be expecting this thing as if like external flow is happening. Air is flowing on the top of this side, right? This is this side of the house, right? So the area of that house side is given as like 4 and 10, which is 40 meters square, right? So that's the area. Now, if you're trying to find the Q value for that side of the house, right? The Q, why I'm saying the Q, see, the air temperature is 5, and it's happening during winter, right? In the winter, even if the house temperature is 20 to 25, whatever it is, outside wall temperature would be like a little bit less, right? It's 12, that's what they're saying, right? Because you're going to lose some heat when the heat is going to pass through the wall. So outside is 12, the air temperature is 5, and then you have those two temperatures. You know Q equal, what is the Q equation? Anybody remember for convection? Q equal HA del T. So the A, did they give you the A? Get heat, right? 40 and, so like 10 and 4, right? So 40 meters square, there's A. What is that del T? Did they give you like 12 and 5, right? 12 degrees Celsius and 5 degrees. That's easy. Your job is to find what? The value of the H, right? So, okay. So, to find the value of the H, you might have already thinking on your head, like, okay, you gotta come up with a correct Nusselt number equation. Because, as you can remember, what is Nusselt number? It is equal to HL divided by K. Now, question is, when I'm saying correct Nusselt number equation, are you after a local Nusselt number equation or a average Nusselt number equation? Are you interested to find a heat transfer for any particular point or the whole side of the wall? The whole wall. So the average. Everybody understand that? So we are after Nusselt number with the bar on the top, average. Okay. So now which one is gonna go? Now they said that temperature of the side of the wall is 12 degrees. So they're saying like, okay, assume it's fixed 12 degrees. So which table you gonna go? Constant surface temperature or isothermal table or constant heat flux table? ISO means isothermal table, right? ISO means same, thermal means temperature. Isothermal means same temperature table, right? So there are like 4 tables right now. So that reduced the 4 table to 2 tables, right? So one is like the turbulent isothermal table, another one is like what? The laminar isothermal table. Now you don't know whether you have laminar or turbulent, which situation to go, but you can decide by finding the Reynolds number. Okay. So you can decide by finding the Reynolds number whether you are dealing with the mixed layer or you are dealing with the laminar layer, right? So if I say the mixed layer, I didn't say it's a turbulent only situation because you see it's a orderly fashion air is blowing on the top. So it could be a mixed layer or it could be a laminar, right? Completely laminar. Now how do you know it's a laminar or mixed? Or how do you know which table to go, laminar or turbulent table? Now you obviously have to find the Reynolds number for the whole side of the house. And when you're going to find the Reynolds number, you know the Reynolds number equation, which is what? Rho VL divided by mu. What is this L again in this case? 10 meter. Everybody understand this? Is it 10 meter? So your L is 10 meter. So the rho, what could be the rho? Rho could be for the air, right? The air is good. So you got to find the rho value. So what else you got to find? The velocity is given, so you don't worry, but you gotta find the mu, viscosity. So these two things you gotta find. rho and mu. Now, if you're going to start flipping the appendix, you'll be seeing they have rho and mu for here. It's all over the places depending on temperatures. So you need to know which temperature to use to find these two values. Which temperature to use? Huh? That's the thing. Anybody remember the film temperature? You're going to find the film temperature. What is the film temperature? The average of this 12 degree and the 5 degree. Okay? And why is this field temperature? Remember, I was saying, like in my undergrad, we used to have 2 lectures per class, right? So with that field temperature, I remember the instructor took 1 class to give you the understanding. I don't have time to give you the understanding of field temperature. But the field temperature, think this way, right? Is the average of these 2 temperatures. So as if like you are getting the temperature very close to the wall, okay? And why is that? I can talk more. If you're going to come, I can talk possibly talk 5-10 minutes about the film temperature, okay? Come to my office if you're more interested. Everybody understand so far? Everybody understand the strategy? Now, if you understand so far, you can actually solve the problem by yourself. Why I'm saying that? You now know which table to go by finding the Reynolds number first, right? By finding the field temperature. And then once you have the table, all you got to do is find the Nusselt number value. Once you have the Nusselt number value, all you got to do find the H value, H bar I'm talking. Once you have the H bar, find the Q, which is H bar A Kelvin. Are you understand? You can solve the problem by yourself? I think so. All right, let's do the problem all together. Okay, so let's start with the givens. So givens. The wall is 10 meter multiplied 4 meters. The surface temperature is given as 12 degrees Celsius. Now, you may want to change it to Kelvin, right? Why? Because when you're gonna try to find the properties, you'll be saying they have the properties like rho and mu. They have those properties in Kelvin in one book. In another book, it's in degrees Celsius. I don't know which book you'd be exploring for properties. Okay, so 12 degrees Celsius is 12 plus 273. Everybody remember that equation? Okay, so which would be 285 Kelvin. Why I said right, TS? Because they did say TS? They didn't. So TS is this, right? You see that? The surface temperature? I don't want to write that. T infinity. T infinity is what? The air temperature, right? So I'm putting it over there. So that they gave this thing as 5 degrees Celsius, which is like 5 plus 273, which would be 278 Kelvin, right?
Would it be okay to do the film temperature and then convert it the answer to Kelvin? It would be the same answer, wouldn't it?
Yeah, the film temperature. The reason I have it in Kelvin because in some appendix you gotta see.
No, I mean like doing the calculation and then still converting it.
Yeah, definitely. Yes, it will be same. It doesn't have any. So the U infinity. Time to time you'll be seeing they give you the U infinity or V. It doesn't matter. Like depending on the convention. Sometimes people use V for Reynolds number. V is the velocity, right? This is the velocity of the air. You can say this is V as well. Okay, in case if you have any confusion. So the V is the same thing, the velocity of the air, right? And then everybody remember how to convert this kilometer to meter and hour to second, right? So we'll be doing that. So I have this kilometer per hour. H means hour, right? So then you'd be converting 1 hour to 3600 second, right? And then 1 kilometer to 1000 meter, right? You do the math, so the kilometer and hour is going to cancel out. You're going to have this 15.3. And by the way, if you don't understand about the value, just to give you an idea, 15.3 is a really high velocity, really high velocity. Okay, it's like a wind gust is coming almost. Okay, so what are the assumptions that you'd like to make here? Yes. Constant properties. Perfect. So Reynolds number critical XC is 500,000. Anything else? Would be neglecting the radiation. RAD dot means radiation, by the way. Negligible. Okay, now another thing, you haven't done it yet, you would be doing it from here. Properties. What are the properties? Reynolds number and Prandtl number property, right? You have to get like the mu, you have to get the like the rho, right? Or I don't know. Do you guys recall the kinematic viscosity? Anybody remember the kinematic viscosity? Kinematic viscosity equation. Viscosity. You have to remember from this point on, because you see in some book appendix they don't have the rho and mu. They have the kinematic viscosity, and this is this is the mu over rho. Mu is what? Dynamic viscosity. In some book, you see the symbol that I wrote, they call nu, N-E-W, nu. You want me to write it? This is not V. This is, they call nu, N-E-W. If I'm not mistaken, it's like nu. Okay. All right. So why I'm saying that, because the properties would be in nu, in Cropera book. Okay. So properties. So first of all, Steve, at what temperature you got to find the property? Film temperature, right? So the film temperature TF, F subscript is for film. Hali, you would like to take that notes, right? So TS, T infinity. You know the benefit of taking notes. If you're gonna write one time, it will gonna type it in your brain. You're not gonna forget. It will help you big time. All right. So 285. Those are two temperatures you have. 278 divided by 2. These are in Kelvin, so you'll have 287.5 Kelvin, right? Hopefully. Is it 287? No, 281. I'm sorry. 281. I'm sorry. So 281.5. All right. So now what are you going to do? You're going to go to the table appendix. Okay. Appendix. I wish I can show it to you. I'm going to show it to you at the end of the class if time allows. But for now, I'll just move on. So if you're going to go to the appendix A4 from, there are like two appendix, right? So you want to go like in Cropera. There are two books I uploaded in Brightspace in Cropera. And depending which books you do have, you're going to find the new. You know what is new? I did talk about it. Let me write it again one more time. No harm. Kinematic viscosity. And this thing sucks. I know whenever I'm writing something, it doesn't show clearly, but in my notes it is so clear, crystal clear. So kinematic viscosity is 1.413 10 to the power minus 3 meter square second. This Prandtl number. Why do you need the Prandtl number? You might have already the idea, right? The equation, Nusselt number equation, does have the Prandtl number. For ER, usually remember it is a little bit less than 1, like 0.7-ish always, right? And then this K. Why do you need this K? Remember the Nusselt number does have K. What is K again? Thermal conductivity. Let me write it. I don't know at what stage you are now. You may forget about this. Let me write it one more time. Prandtl DLT number, right? Okay, so this K is 0.02428. Remember, that was the thing that you were confusing with the Biot number and this Nusselt number, right? This K is for ER, right? Everybody remember that? The K is for ER. All right, so then the solution. Okay, and don't worry, I'm gonna give you time to catch up, and we'll all go together. Okay, it's not like I'm gonna go first and we're gonna go a little later. So this house does have so many things, right? This side of the wall that we are interested only, right? And only the outside side of the wall, right? Not even the inside side of the wall, right? So then you have this thing is 10. You can say this is L, and this is what 4. Okay, and you know this ER is coming along this direction, and you know you have this U infinity, right? And T infinity here. And you know the boundary layer would be like something like that, right? I don't want to draw the boundary layer on the top, but you can assume what is happening on the top of it. All right, so then this temperature here, sorry, is TS. That's the surface temperature, right? You understand so far? And then this Q equation is equal h bar A Ts minus T infinity. So that's what you're trying to find, heat rate. You'd like to write the main equation first. And maybe you want to say this is your equation 1. Okay, now to find that, I was talking about it already. I'm writing it as well. So you gotta go with either constant temperature or isothermal versus constant heat flux. So which table, right? Or this is isothermal. Okay, you gotta decide that. You gotta decide whether it is laminar so it's laminar versus mixed layer. You gotta decide on that as well. When I'm saying mixed layer, it is laminar plus turbulent. TURB means turbulent, right? LM means laminar. Okay, you got to decide on that, right? So how you going to decide all of this? You got to decide by finding the Reynolds number L, okay, and you're going to compare it with Reynolds number XC. What is the Reynolds number XC or critical Reynolds number, Isaac? Remember? It's 500,000, right? So you got to find the Reynolds number for the side of the wall. How are you going to find the Reynolds number for the side of the wall? So let me write that. Airflow parallel to 10 meter, right? You want to take the cluster 10 meter side of the wall. I promise I'm going to give you time to catch up. All right, so then Reynolds number is equal to U infinity. I know this is U infinity rho L divided by mu. You can write it this way, right? Or U infinity is the V, is the same thing, right? Or you can write it U infinity L over nu. It's the same thing, right? Okay, I'm gonna stop it here. I know you guys are taking class notes. Okay, I kind of make it a little fast. Okay, so catch up with the class note. Let me know when you're done. So I can move on. Okay. At this point. Okay. Now those who are advanced, you can actually literally solve it. Why? What are you gonna do? To give it a spread. It's spread. You find the Reynolds number. You compare those two, right? Once you compare those two, you figure it out. Okay, I'm dealing with mixed layer, right? If you're dealing, it is the mixed layer problem. So if you're dealing with the mixed layer, then you've got to go to the table where the mixed layer Nusselt number equation is. So use that equation to find the Nusselt number. Once you have the Nusselt number, remember on the mixed layer A value is 871. Okay, I did talk about it. So once you have the Nusselt number, find the H and find the Q. So yeah, those who are feeling like understand everything, good graphs on it, just do it that way. Those who need more understanding, just take the class note, let me know when you're done. So I'm gonna move on so you can catch with me. Okay. I think you're done with the class note.
Yeah.
Finish the class note, everybody. Matt, you're done with the class note? Chelsea, you're done with the class note? Everyone's done with the class note? Should I move on? Alright, so I'm moving on. My notes goes away. All right, so the Reynolds number, once we're going to plug all the values, okay. So the Reynolds number, you're going to be finding, so you have a velocity 15.3 meter per second. Remember, I was talking about the 15.3, it's a huge velocity, it's like a wind gust, right? So 10 meter divided by this nu, right? So this nu is 1.413 10 to the power, is it 10 to the power minus 3? I think I did 10 to the power minus 3, yes, meter square, yeah, meter square per second. Then you're going to have a value of 1.081 10 to the power minus 10 to the power 7. So this Reynolds number is definitely greater than Reynolds number critical. So I can say we are dealing with a mixed boundary layer. So we are dealing with a mixed boundary laminar plus turbulent. Okay, you got it so far? All right, so then step 2. So combine laminar and turbulent layer. What is that? It's a mixed layer, right? So dealing with combined, right? So then the average Nusselt number is equal 0.037 Reynolds number to the power 0.8 minus 871, right? And the whole thing will gonna be Prandtl 1/3, and then you're gonna plug all the values. So which would be 1. Reynolds number. What did you find? 0.8, right? 871, and then 0.734 1/3, which would be 1.336. Sorry, is that the value found? 10 to the power 4. You have a higher number? So
the number is right, but the superscript.
Superscript is a little different.
Yeah.
We'll see it shortly. Let me plug all the values, right? So you have this 0.024. What is the K?
Our K was 0.02428.
428 or 10 meter, 1.336, 10.4. Okay, so then 32.43 watt per meter square Kelvin. Okay, and then you can find the value of the Q, heat rate, for this side of the wall, which would be H bar A Ts minus T infinity, which would be 32.43 watt per meter square Kelvin, 10 meter, 4 meter, 12 minus 5. You can say this is same as like Kelvin, right? And then the value should be 908. I don't know, for some reason my note doesn't have. Anybody got the value? Is it like 908 kilowatt or 90 kilowatt? Maybe 90 kilowatt. What did the value got? 9.1. I have for some reason 90 kilowatt. I don't know. So this one, let me put it this way: 90 to the power 3. So 90 kilowatt, and put a question mark. I'll talk about it in next time, but you got to check the math. As long as the math goes correctly, then you should be getting the value. I'm sorry, I've got a little overboard, but to give you like the overview of the whole problem, basically it is very straightforward. You just have to find the Reynolds number. If the Reynolds number is more than the critical Reynolds number, you just have to find the correct equation for the finding Nusselt number, which is a mixed layer Nusselt number equation. Make sure you know the A value is 871, right? Or you can calculate it, and the equation numbers for the book is there as well. Once you have the value of the Nusselt number, you find the value of the H. Once you have the value of the H, you find the value of the Q. Okay, that's it. All right, guys. I'm not gonna see you next week, right? Because Tuesday and Thursday I won't be here. I'll be conference. If you have time, just walk with me. I'm gonna show you how to do with the experiment for the project. If you're interested, if not, then it's fine. I'll come back on week 13. You can do it, or I'll be here next week on Friday as well, on Monday as well. So
I have a thermocouple and a torch. And do I have to do it right now?
if you have a thermocouple meter, I mean, I do it. You have to set up. You can do it right away. You have a torch and thermocouple meter. Thermocouple meter is in HVAC lab. You can do it right away. Yeah, just finish it. Huh? What? Oh yeah, I can share. I can upload it right away. I do have everything. like you know.
You know the temperature reading guns, the laser that reads the temperature.
No, hot gun. You know, the Kevlar, something like that.
No. The it shoots a laser and reads the temperature of a surface. Is that accurate enough to use, or do we need to use a thermocouple?
Oh no, you gotta use thermocouple.
It has to be a thermocouple.
Yeah, the setup is with the thermocouple already. You just take a thermocouple meter.
So if we have all the equipment, can we do it by ourselves? Like,
Yeah,
Sure,
definitely.
sure.
But you'd like to talk with me first, so I'd like to show it to you at least, like what things are, how to do it. So that way there won't be any confusion. Otherwise, other instructors say like, if you did not when I was walking and you see me, wandering here and there and asking questions, he got mad, he sent me an email, or what is happening with your student. I don't want this kind of scenario. Okay, I want you to talk with me, so I explain everything, so you can do it by yourself. And then if you have questions, then ask people. Okay.
Yeah.
Okay. At least I'd like to show it to you what is happening.
I wasn't trying to force you onto our team.
Ask both. Yeah.